And welcome to a short video on section 5.5, which is about disproving existence statements. And it also is an excuse to practice with proof by contradiction a little bit more. So this is kind of a mirror section to section 5.1, which was about disproving for all statements. And in section 5.1, if you want to disprove a for all, it involves manufacturing a counterexample, a single counterexample. In this section, you can't do that now because disproving existence means proving a for all, because existence and for all are the opposites of each other. And so even though we're disproving things here, we're not going to be manufacturing counterexamples, because if you want to disprove existence, it means prove for all. So I want to show you two examples like that. So essentially what I'm saying is, if somebody says to you, hey, justify to me why this is false. There exists something in S such that some statement P of X. Prove that's false. Well, then what they're really saying is, if you not this, you get something true. But when you not a there exists, as we've talked about plenty of times now, that turns it into a for all. And so what you're really being asked to think about is, how could I justify this? For everything in S, not px. So let's look at two examples like that. So suppose you're asked to disprove this. There is some odd integer n such that the square of that plus 2n plus 3 is odd. So that's an existence statement. So disprove that. So if we not that, what we're saying is, oh, what we actually need to do is justify this statement. For any odd integer, n squared plus 2n plus 3 is not odd, is even. And so if you like, we're being asked sort of a backhanded way to think about this statement. If n is not an integer, then n squared plus 2n plus 3 is even. And that's something we can prove. So we prove it just like we do before. But again, I just want to emphasize here, since we're disproving an existence statement, we can't just like do a counterexample. We can't say, oh, well, notice n equals 5 doesn't work, right? Because if you want to prove this is wrong, you'd have to justify why no odd integer works. So here's a proof of that. If n is odd, then n equals 2k plus 1 for some integer. And then you can just do our normal thing, like we're being asked to think about n squared plus 2n plus 3. So let's think about it. Here we go. N squared plus 2n plus 3 equals, there's n squared, there's 2n plus 3. And if you write this all out, expand it out, you get 2 times something. So there you go. If n is odd, then n squared plus 2n plus 3 is even. And we've disproved this statement. Right? The statement is false because for any odd integer, n squared plus 2n plus 3 is even. Okay, so there's an example of disproving an existence statement. And then let me show you one that involves proof by contradiction. This is not an example in the text, but I like it anyway. It's sort of cute. So consider this. You're asked to prove there do not exist positive integers a and n such that a squared plus 3 equals 3 to the n. There do not exist positive integers. So this is still an existence statement, right? It's about existence. But whenever you're asked to prove there don't exist something, proof by contradiction is often very natural as a proof technique, because then you just say, well, I mean, suppose such things did exist. Like suppose I did have an a and an n such that this happened. And that gives you an equation in this case to work with. Like you can get your hands on something, you know, like, well, what if that thing did exist? Let's investigate the consequences of that. So again, to disprove this existence statement, we just not this and see if we can prove that. And we're going to prove it by contradiction. So assume, to the contrary, I could actually manufacture integers a and n such that this equation holds. Let's see if we can investigate the consequences. And so when you're dealing with an equation like this, by the way, it can be not clear what to do. But one thing you don't want to do, as we've discussed before, you don't want to do things that might turn integers into non-integers. So like, you don't want to isolate a squared and then take its square root. Because if you do that, like 3 to the n minus 3, you don't know if the root of that is in the integers or not necessarily. Right? You got to be careful with stuff like that. But anyway, you might notice here that if you do isolate a squared, if you write a squared equals 3 to the n minus 3, you learn pretty quickly that a squared is a multiple of 3. And so here, a squared equals 3 to the n minus 3, which implies a squared equals 3. And with things like this, by the way, you have to be careful. 3 to the n minus 1. Because somebody could ask you, how do you know that's an integer? Like we just said, we have to be careful about leaving the integers. How do you know 3 to the n minus 1 is an integer? And the answer is because n was assumed to be positive. So n is at least 1. And so this is at least 0. So worst case scenario, this is 3 to the 0, which equals 1. You're not dealing with like 3 to the negative 2 or 3 to the negative 3, something like that. So this is okay right here. I'm using the assumption that n is positive to say that a squared is a multiple of 3. Anyway, so since n is a positive integer, 3 to the n minus 1 is an integer. Thus, 3 to the n minus 2 to the n minus 1 minus 1 is an integer. And that implies that a squared is a multiple of 3. We know from your previous quiz, I believe, that if 3 divides a squared, then 3 also divides a. So we get pretty quickly that actually a itself is a multiple of 3. So this equation, basically, if we are allowed to assume it for the sake of contradiction, we learn pretty quickly that a is a multiple of 3. And now, like, we're sort of cooking with gas here because we have an equation involving a. So maybe we can see from this what the consequences are. Now remember, we assumed this equation right here. A squared plus 3 equals 3 to the n. We assumed that to try to get a contradiction. So, and now we know what a is. A is 3k. So let's plug that in and see what we get. So a squared plus 3 equals 3 to the n. Okay. Oh, I see. I shouldn't skip steps because I'm too sleepy to understand what happened here. But basically, if you expand this out, you get 9k squared, but then you divide everything by 3. So here you go. You take the left-hand equation, divide everything by 3, that's what you get. And then we get this. Okay, that 1 is equal to 3 to the n minus 1 minus 3k squared. And so this should sort of ring alarm bells a little bit for you, because what this is saying, basically, like, if you look at the right-hand side, the right-hand side should be a multiple of 3, right? A power of 3 minus 3 times something. And you know what's not a multiple of 3? Is the number 1. Okay? 1 is definitely not a multiple of 3. So surely we have some sort of contradiction here, but we got to be a little careful, because to say 1 is a multiple of 3, we have to write it like this. Like, we kind of just want to factor out a 3, don't we? And be like, look, see, 1 is a multiple of 3. 1 equals 3 times something. But if you do that, you end up with a 3 to the n minus 2. And again, you can't leave the integers, so you got to be careful here. So 3 to the n minus 2, since n is positive, the only way that you might leave the integers is if n equals 1, and then you have a third right here. So all of that to say, you should treat n equals 1 as its own case, so that then, if n isn't equal to 1, you can write this down and not worry about it. This 3 to the n minus 2. So that's why here I have n equals 1 separated out as its own thing. So if n equals 1, then this equation looks like 1 equals 1 minus 3k squared, which would imply that k is 0, right? Because you get 3k squared equals 0. But if k is 0, right, a is 3k. If k is 0, then a is 0. But a is positive. We set it up here, right? A is positive. So if n equals 1, we get a contradiction. So n can't be 1. So since n is bigger than 1, this 3 to the n minus 2 thing is not troublesome. And now I can go back to this equation here and factor out my 3. And I can write 1 equals 3 times stuff. That's bad, because let me tell you, 1 is not 3 times stuff over the integers, right? 1 is not a multiple of 3. It's a divisor of 3, right? 1 is a divisor of anything, but 1 is not a multiple of 3. So, but if this equation were true, it would be saying that 3 divides 1. 3 is a divisor of 1. And that's not true. So we get a contradiction. So we assumed we could find positive integers a and n that made this equation work. And from that assumption, we blew everything up in our face, right? We caused math to collapse. which you can't do. Can't make math collapse. Otherwise, I wouldn't have a job. So shame on you for trying to do that. But I do have a job, right? So contradiction, and we're done. Okay, so I wanted to show this to you, to show you another proof by contradiction, but also because of the subtlety. Like, you do need to be careful if you start factoring things out and writing things down like this. We are living in the land of the integers in this problem, right? Integers. So you have to justify why this is okay to write down, which I do very carefully. See how carefully I did all that, right? And also this proof, this is it's kind of subtle, right? So like noticing that a squared is a multiple of 3, which means that a is a multiple of 3, and then exploiting that to eventually get our contradiction at the end. That's not an easy thing to think of. That requires some creativity. So again, I'm not showing you my scratch work here. So I just took this as a fresh problem myself. This is a problem from the book in the exercises, but I didn't look at the solutions. I just thought, oh, I wonder how I would do this. And so for me, I just immediately see like, oh, a squared plus a multiple of 3 equals a multiple of 3. Thus, a squared should be a multiple of 3. So a should be a multiple of 3. You know, so you can kind of get that logic going, and then hopefully you can exploit that. But it does take some practice getting used to, right? None of this is natural when you haven't done it before. Okay, so that's all that section 5.3 is about. There are a couple more examples in the book you can read if you want to, but just pointing out that to disprove an existence statement, really you're proving a for all statement. And that last example I showed you, the not was in the existence itself. So I got a not of a not. So what I'm saying is, like basically for all positive integers, right? You can't get this equation going. Okay, so that's the end of section 5.5 and also the end of chapter 5.